Welcome to another unit in business mathematics. In this unit, I'm going to talk about integration, or rather about how to calculate an indefinite integral of a function. Let's have a closer look at this. Here, as exercise, we have calculate the following indefinite integrals. Then we have four different functions, which here is the integral over x to the power of 3, the integral over 3x to the power of 3, the integral over, in parentheses, x to the power of 3 minus 1 squared, and finally x to the power of 6 plus 2x to the power of 3 plus 1. Well, let's start with the first one. With the integral over x to the power of 3 dx. Here, we can do this relatively easy and straightforward because we already know the rule for working with polynomial expressions. So with something which reads as x to the power of n. In this context, what we're doing here is we simply take a look at the exponent, increase the exponent by 1, so from x to the power of 3 we get to x to the power of 4. And then we divide this by this new exponent. So we divide this by 4, or as done here, multiply with 1 divided by 4, so the inverse of the 4. And before we're done with this, we add a plus c here. Why the plus c? Because we can imagine the procedure here as if we were to take the derivative of this expression, we would have to end up at this function here. Well, if this is any type of number or constant, this actually would be eliminated by taking the first derivative. So it could be the case, if I work my way back, that there has been or should have been some kind of constant or number here. So to take care of this, I'm always adding a plus c to any type of indefinite integral, or if I'm calculating the primitive of a function. Well, with this very straightforward, easy introductory example, we can then go over to part B, which is only a slight expansion to the exercise before. What we did here is one thing which is new. So we have a number, the 3, in front of our expression here. And whenever we have multiplied some kind of function with a number or some kind of constant, so with anything which is not dependent on our variable here, so on the x, what we can do is actually the same thing what if we work with a sum we would call factoring out. So what we do here, we pull the 3 in front of the integral. That's what we do here. And then we can simply calculate this integral, which we actually did on the slide before. So this integral gives us 1/4 x to the power of 4. And we multiply this expression with 3. Once we're done with this, at the end, we again add plus c. Now you might say, well, this expression already has a plus c. So wouldn't it have to be 3c, which I add here? Well, c is just a general expression. Could be anything. So it doesn't matter if I write 1c, 2c, 4c, 3c, whatever. So I'm just writing this as one general expression at the end after I finish calculating the stuff in front. So this, whatever is written in front of the integral, does not impact the c. Or even if I have two integrals, I will get only 1 plus c. That's just an arbitrary term which could express any type of constant. Well, once we have this, the only thing left here in this context would be to simplify this by pulling the 3 up into the fraction. So writing this as 3/4 x to the power of 4. Well, that was already part 2. In part 3, we're going to learn something new, which however relates to what we did in B. And that's when we have an expression like this here, we can first use the second binomial form, which then would give us x to the power of 3 squared, so x to the power of 6, minus the second binomial form, 2 times x to the power of 3 times 1, giving us this here, plus minus 1 squared, giving us the plus 1 here. Now we have different terms connected with minus and plus. So what we can do here is we can apply the integral to any of these 3 parts separately, always connecting it with the signs we have in between here. So we can split up this integral into 3 partial integrals. To the first one, which is only x to the power of 6, then minus, then 2x to the power of 3. That's actually the expression we had in B, or more or less the same expression we had in B. In B we had a 3, now we have 2. So we can pull this 2 in front here again. Finally, we're left with the integral over 1. Well, once you got the formula for getting the primitive of x to the power of n, it should be relatively straightforward what we do in the first 2 examples. So here we increase the exponent by 1, giving us x to the power of 7, and we divide by this 7, giving us 1/7 here. Here we have x to the power of 3, increase this by 1, have x to the power of 4, divide by this 4. And now we're left with the 1. The 1, however, can also be imagined as an x to the power of 0, because everything to the power of 0 always becomes 1. So if I have a 1, I can also write it as x to the power of 0. Then I would increase the 0 by 1, so I will get x to the power of 1 divided by this 1. Well, this just gives plus x. So the integral, the primitive of 1 is x. We put the 2 we have here in front of the integral, in front of this primitive again. And finally, we add a plus c. Well, the only thing left to simplify this would be to actually combine the 2 and the 1/4 into 1/2, which then would look like this. And that's already everything to part C. And part D actually is pretty similar. Here again, I can split this up. The only difference being now I have a plus and not a minus. But in the end, it's exactly the same arguments I had before. So the 2 here in front, I will then combine with the 1/4, giving me more or less the same result. So all of this works pretty fine, as long as different parts of functions are either connected with plus or minus, or, as in this case, I multiply a base function with a number or a constant. Then I could just pull this in front and consider only this part by itself. Well, we already know these rules because that's the linearity rule or rules we already know from derivatives, from working with derivatives. Well, more or less similar rules exist for integration as well. So we have this linearity rule, and in the later session, we are also going to talk about the counterparts to, first off, the product rule, and second, the chain rule. However, regarding this unit, we are at the end, so I hope you enjoyed it. And if you want to see more, feel free to visit the rest of this course. Else, I say goodbye and see you next time.